The last talk for this workshop will be given by Karim Adiprasito, who will give an outlook. Karim?
Okay, I think first of all, let's thank the junior speakers, so the two Pauls and Simin and Dasha and Andrew that gave excellent talks. It was kind of an excellent contribution to the workshop. Also, I think we should give some applause for Stavros, who gave 3 amazing talks. And finally, and I mean, last but not least, as one says, I mean, I'm sorry for not being there, and Vaso has been an amazing replacement, and I think we should all give her some applause. You know, thank you for keeping this up and keeping everything in line. That was amazing. All right, I wanted to give a little bit of an outlook. So the idea was that I also should, okay, I should also thank Imsa and Natalia and Diana or Danya for making this all possible. So before that, okay. So what do I want to talk about? I want to give a little bit of an outlook of some open problems, of some recent results, of some new developments, and I want to focus in particular on two kind of different things that one is kind of still within the kind of realm of Lefschetz theory and this combinatorial commutative algebra, and the other one is kind of asking, well, what happens beyond Lefschetz theory, and how do we go from here? So I want to specifically talk a little bit about Stanley's conjecture. And of course, Stanley has several conjectures, so I will kind of Stanley conjecture.
Are you aware that you're writing?
Sorry?
You should your paper.
Yep, that's my fault.
And then we're going to receive that in the wrong direction.
Yeah. On Stanley conjecture. So we saw two kind of key two results, or actually we saw several results within Lefschetz theory in the past days, and one of the key results was that if I pick a triangulated sphere, right? So triangulated sphere sigma, and what else do I want? I have a triangulated sphere sigma, and I have associated to it this Stanley Riesner ring, K of sigma. Right? Then what I look at is this Artinian reduction A theta of sigma. And I want to know some numerical properties of the Hilbert polynomial of this, right? I mean, I know by basic commutative algebra that questions about the phase vector are encoded here and then are encoded here. And so I want to know some properties here, and usually these properties reduce to the Hart-Lefschetz theorem, right? So we want the Hart-Lefschetz theorem for a theta sigma. Okay. So that is one result, and this is proven by myself, and then Papadakis and Petrotu in a slightly different generality, and then in the highest generality by myself together with Papadakis and Petrotu. And this is about this. I mean, if you just want spheres, these are the two to read. I mean, this here goes a bit beyond. It goes to cycles. We don't really have to go into cycles. Star Wars already explained a little bit of framework today. Okay. And another context that we have here is the case of lattice polytopes. So if P is a Gorenstein lattice polytope, well, then there is something called a semigroup algebra associated to it. And the semigroup algebra also satisfies a version of the Lefschetz theorem. Or at least, first of all, the semigroup algebra kind of behaves like the ring of the ring of a simple sphere. So what do you do? So once again, somehow it's a rather simple construction. If P is a lattice polytope, all right, so here's my lattice polytope. It contains lattice points. Then I can take another point at the origin. And take the cone over that. And then I have a semigroup algebra associated to this cone, K of P, semigroup algebra. All right. And this semigroup algebra satisfies, okay, so it's semigroup algebra if this semigroup algebra KP is standard and Gorenstein, then one can look at the Artinian reduction, AK of P, and this Artinian reduction has a property that it satisfies the Lefschetz property. All right, this has a Lefschetz property. This has Lefschetz property. And this is also a recent work of this slightly enlarged team. All right. So this object is nice in the sense that this K of KP is an integral domain. And so Stanley conjectured if R is an integral, right? The standard graded integral domain, then the associated Artinian reduction A of R theta has unimodal Hilbert polynomial. All right, so that's kind of a generalization of this fact. All right, so it generalizes this fact. And the more we think about it, I mean, first of all, we are not quite sure whether this can be true, but the more that we think about it, here's somehow we wanted to have a more conceptual generalization of this lattice polytope result and the Stanley-Riesner ring result. But of course, if I look at the Stanley-Riesner ring, K of sigma, it's not in the integral domain, right? Is not an integral domain. Okay. And so we have this work by on spheres, all right, by essentially the team, and then this work that is additionally with Johanna Steinmeier, which does the lattice polytope case. But somehow in some way, I mean, they don't have a common generalization. So Stanley conjectured that integral domains should be good, but what we think is maybe the better way to think about all of this is reduced strings. So let me not reduce it. The integral domain. And so I want to introduce a conjecture based on this property. So what is reduced? Reduced means, right? Reduced just means there are no nilpotent elements. So if U is not 0 in K sigma, then U to the I is not 0 in K sigma. Right? So there's no nilpotent elements. Integral domain, I mean, clearly I can't hope for that, but that somehow that powers are not 0, that's certainly true. And of course, it kind of, I mean, that's kind of the natural thing to ask, right? If you want anisotropy, you really have to have this property. Otherwise, if you don't have this reducedness property, you can forget anisotropy in any case. So let's make a conjecture or question. And I guess it's somehow that's something that we all asked ourselves. A P P is if R is standard. Again, this just means generated in degree one graded commutative ring. Is it true that if it's a standard graded commutative ring, sorry, is it true that okay, I want one more property of positive cool dimension. So I don't want this to be small, already reduced of positive cool dimension. I mean, in principle, that's contained in reduced, but it's also cool dimension graded and reduced commutative ring. I mean, in principle, that's contained. The cool dimension is a theta of sigma. Sorry, not a theta of sigma. So the Artinian reduction R, which is just R modulo theta, anisotropic for generic theta. And I think that's a neat conjecture because it could generalize all the previous conjectures that we had. All right, that's a nice thing.
Excuse me,
so
I have a question about the definition of reduced. So, so is there any upper bound on the I?
no. You have all powers are non-zero. Of course, I mean, yeah. I mean, it doesn't really matter.
But it must be at least at the most to the Soko degree.
No, but it's okay. So this here has no Soko in general, right? I mean,
okay.
it's before the Artinian reduction.
Okay, I understand.
All right. So it's the Stanley-Riesner ring before the Artinian reduction. And it is it's Stanley-Riesner ring before the Artinian reduction, and it is the semigroup algebra before the Artinian reduction. So this can be this might not have a Sokal in general, right? Because you can have element. I mean, you have cases where there is a Sokal. In general, these two cases don't have Sokal. Right, and that's a question, right? Somehow, if you allow for that, if you have a reduced ring, right, that is sufficiently nice or standard graded, commutative, is it still reduced or as reduced as possible after the affinity reduction? So let me give you a partial, I mean, not even the evidence, like just a intuition why it might be true. So if R is reduced as above, as before, and L in R1, R1 is in a linear form, or yeah, is generic such that R modulo L is of positive equal dimension. So basically, the codimension of R has to be at least 2, and I take out one element. Then we can choose. R modulo L so that it is reduced. So it really just depends on the last, the sum of this last Artinian reduction. Okay. Is that okay? Okay. And yeah, so that's a conjecture. One of the cooler questions that somehow is always interesting in this context is, well, I mean, if we want to generalize this, what we had until now, in some way, we need to understand, we need to go back and understand the volume polynomial. So the question is, what is the volume polynomial of this ring modulo theta? Right? How do I normalize that? And that's not so clear how to give a canonical normalization if I just give theta like that, right? But let's assume again, so we had this trick all the time where instead of looking at okay, so what was the volume polynomial, right? This was, if I look at the Sokal degree, so if theta is a Sokal degree, D is a Sokal degree, or D is a Sokal degree, then volume polynomial was its identification with the base field. All right, so R was this function. And so the question you could ask is, well, how do I do this beyond? How do I do this beyond this special case of steady Reasoner rings? Or how does this work in other cases? And here's somehow Stavros and Vaso, they gave you a nice intuition, and I want to give you one more intuition that we learned from Frank Olaf Steyer. So the intuition comes from the following, all right? So we are looking at this polynomial ring in some variables, right? So R is a ring over, right, is a module over some basic polynomial ring. But then, okay, so we wanted to enlarge this ring, right? We want to introduce some new variables, right? We want to introduce some new variables, and specifically we want to introduce this ring over K theta ij, where theta ij are the coefficients of the linear system of parameters. Okay? And now, right, in some way we want to have the volume polynomial be a rational function, so volume of R theta to this larger field, K theta, should be a rational function in these theta I. Okay, and in particular, it should be in some way a minimal representation or a local representation. And here's there was a conjecture or a question that it's a suggestion or in the last talk by Stavros that this might have to have something to do with this Kuste-Milan projection, and I want to give you just an equivalent way of saying this due to Frank Rudolf Schreier, so F.O. Schreier. Okay, and the result is the idea is as follows. Let's not look at K theta x. So let's forget that. Let's look instead at K theta and x together as variables. Okay, so this is a polynomial ring in the theta and x. And then I have my ring over, right? R is a ring over this. Okay, this is I'm living over this larger ring. And now what can I do, right? I can look at R and I can, okay, so naturally I can write down a minimal resolution over this, let's call it S, right? That's a minimal, I can write down a minimal resolution of this over this new ring. All right. But let me consider actually a minimal resolution, a minimal free resolution of K modulo theta. Okay. So that's a nice state object. And then I can also look at a minimal resolution of this ring modulo all my original variables and can write on this minimal resolution. Okay. And by basic homological algebra, these minimal free resolutions, they end at the same step. They end at the same location. And again, by basic homological algebra, there's a natural map between these two free resolutions. And I could call this map psi. Okay. And now what I want to normalize the volume, right? I want to say that the volume of an element is normalized such that if I take this element, right, I want to look at psi of x, and that this should be equal to 1. And that's a normalization that Stavros suggested in the last talk. That's where it should come from. That's somehow the suggestion, right? Somehow this is a suggestion of normalization. And at least in this, in the works that we have, in the works that we understand, that's the right normalization, suggestion of normalization for the volume. Okay. And that's what I wanted to talk about in this direction. It's not this in the direction of combinatorial commutative algebra. And what I want to talk about next is a little bit about a different conjecture, and this is called the Cheney-Davis and Gall and Van Den conjectures. So beyond Lefschetz. Okay. And this has to do with a special class of triangulated spheres, and this is so-called flag spheres. So sigma flag sphere. Okay. So what is flag again? Flag means that the triangulation is the clique complex of its one skeleton. Clique of one skeleton. Okay. And so in other words, right, I mean, you probably all know this, that if I see a triangle, if I see the one skeleton of a triangle, then the boundary, then the interior of the triangle has to be there. If I see the boundary of a tetrahedron, then the interior has to be there. So that's a flag sphere. So the smallest flag sphere in each dimension is the boundary of the cross polytope. Boundary of cross polytope. So the smallest flag sphere in dimension 1 would be the square. The smallest flag sphere of dimension 2 would be the octahedron, or the boundary of the octahedron, and so on and so forth. And there was a certain observation that if you look at flag spheres, the H vector satisfies or seem to satisfy a much stronger version of the lower bound theorem. Specifically, people observed the following. They wrote down the H vector, so H0, H1, H2, H3, H4. And what they observed, okay, so they wrote this down, 1, 7, 20, 7, 1. And then they observed that this is much larger, right? It's much larger than that's what the lower bound theorem predicted. And so what they did is they decomposed it into other vectors. So the Lefschetz decomposition, what you usually do to get the G vector would be to write this vector as a linear combination of these here. Right? And if I write this as a linear combination, then the coefficients that I get here, well, this is 1, this would be 6, and this would be then, okay, so it should be just 13. Then what I get here are the G vector. So this is G0, G1, G2. Right? So they are very non-trivial. What they observed, though, is that perhaps you can decompose it into different. Let me actually keep it here. So G0, 6, 13, G1, G2. Okay. All right. And so what is what is known about these results? What else can I do? Right? Well, I mean, they noticed that I can decompose it into other vectors. So I could write it in terms of binomial coefficients. So 1, 4, 6, 4, 1. Right? And then what I get, if I write it in terms of these vectors, I get different numbers. I get 1 here, I get 3 here, and I get 8 here. And these, they called the gamma numbers, gamma 0, gamma 1, and gamma 2. And Brennan and Gall conjectured conjecture by Brennan and Gall. This these numbers gamma I are non-negative for each of the or for each flex here. Okay, and that's a conjecture. And the main question though is what is an interpretation for these gamma numbers? So what is an algebraic interpretation for these gamma I? Okay. Okay, what can be done? What's this is an open question. So open question. All right. There's no clear candidate for doing this. We don't know how to algebraically approach this. So there seems to be no algebraic interpretation for the gamma I. Well, except for one case, if so, theorem by Karim is that if sigma is order complex of a Gorenstein coset, then the gamma i's are dimensions of some sheaf. Let me not go into that. The dimensions of some sheaf. Okay. So here's some algebraic interpretation. I will not go into the details, but if it's a poset, then you can indeed get some interpretation. That's good. I mean, that's cool. But it's I mean, this is one of the coolest open questions, and I'm still thinking about it. And also with Davos and with Vaso, we kind of try to access it. We have no clue at the moment. But I mean, it's a one. If you prove this, if you provide an algebraic interpretation for this, it would be very cool. So let me try to give you a different interpretation or a different way of accessing these gamma numbers that kind of transforms them into other numbers, and then we have an interpretation. Okay. So what we do now is, okay, so let's associate a different space. Okay. And what is the different space? It is the so-called Dancer complex, or the Dancer manifold of a simplicial complex. So given delta, a simplicial complex on vertex set n, what we can do is we can associate a cubical complex. Associate a cubical complex, C of n. Okay, First of all, the original C of n is just the n cube, is the n-dimensional cube, right? 0, 1 to the n, right? But now I want to associate a subcomplex of this cube complex in a kind of in an intelligent way. And how do I do that? Well, I pick delta. Pick now delta. And think of it as somehow think of it as realized on the vectors on the vertices E1 to En. So these are just the basis vectors. So this is in Rn. All right. So these are the basis vectors. In Rn. Okay. And now let me complete the picture. So let's say I have my simplicial complex is this one, 1, 2, 3. And then I have my basis vectors 1, 2, and 3. 1, 2, and 3. Right? And what can we do with these? Well, I mean, what we want to do is now use them to define a subcomplex of my cube. So my cube also sits in the space. All right, so it's spanned by these basis vectors. It consists, so dancer of delta consists of those tau in this cube, Cn, such that the affine span of tau is parallel to the span of sigma for some sigma in delta. So specifically, I mean, in our case, what would this look like? Well, in our case, we would have these vertical pillars and the bottom and the top. Okay, so that is how I. All right. So if delta is a flag sphere, then dancer of delta is a non-positively curved manifold. And this manifold has a cohomology ring, H D of delta. Okay. Okay. And this manifold, okay, so this cohomology ring, it has a Betti vector. We can also write it down. It's again some symmetric thing. So 1, 7, 20, 7, 1. And we could again try to write it in terms of these symmetric vectors. And again, it would turn out that it seems that the gamma numbers that I get here, right, which are different gamma numbers, these gamma numbers are non-negative. Okay, it would seem that this is the case. These are different gamma numbers. There's a relation between them, but I mean, a priori they're different. Okay, seems that these gamma numbers are non-negative. Okay. However, in this case, there's actually a sensible algebraic interpretation, because what we could ask is, perhaps there's an algebraic reason this time. So could there be some reason? Could there be some interpretation? What is different this time, but would allow for interpretation? Well, here's something that could work, right? So H, perhaps this cohomology ring of D of delta has a decomposition into exterior algebras. So what do I mean by that? Well, it could be that I have a decomposition as follows. I look at my cohomology ring, right? I look at H, and I want to write it as the direct sum of some spaces Bi and exterior algebras alpha I. Right? What do I mean by that? So I here, let me do it. J and I, J goes from J equals 1 to D minus 2I. Okay. So this could be a possible decomposition, and in particular, if I have this decomposition for Bi subspace of Hi subspace, and these alpha i's in H1, then what you get is that exactly, I mean, if you compute the exterior, the dimension of these exterior products, then you get exactly Bi to, well, what to what will you get Bi to the then you got exactly that the dimension of Bi, sorry, it's a little late for me. The dimension of Bi is equal to this gamma I in the sense of this aforementioned space. So gamma I is more, let me write it specifically, gamma I of the Dancer complex of delta. All right, so gamma I of Dancer complex of delta. All right, so this is an algebraic interpretation. Unfortunately, it does not seem that there is a corresponding algebraic interpretation in the case of the in the case of the Stanley-Wiesner rings, because we don't know how to embed exterior algebras, right? We don't know how to embed an exterior algebra into a commutative ring. It's an anti-commutative object. So we don't know how to do that. But it turns out the theorem myself recently is that indeed this Boolean decomposition exists. Boolean decomposition exists for delta PL flags here. All right. It's one interpretation. It's kind of a different interpretation than gamma numbers. I wonder whether in some way whether in some way there's an algebraic way to go back to the standing reasoning. I don't know, but it's a neat thing. So the question is, right? So I have the exterior algebra, and I have the symmetric algebra, which is just the polynomial rings. Right? This is a commutative world, and I have the anti-commutative world. The question is there some way of seeing this Boolean decomposition in a tensor algebra and transfer this from one to the other? I don't know. Okay, that's a big open question, and we're currently working on it. But also, if you just find a Boolean decomposition or some analog of this Boolean decomposition in the symmetric ring, that would already be very cool. We just don't know. And those are things that I'm currently thinking about, right? To summarize, kind of, we want to understand this volume polynomial on a deeper level. That's the first question, the first part. Does it work for reduced strings? Does it generalize these marvelous results with my co-authors, Stavros and Vaso and Johanna? What happens? What does this Boolean decomposition mean? Is there some symmetric analog? Is there some decomposition into cohomology rings of complex products of projective spaces? That's kind of the point. Anyway, that's where I wanted to close. I think I have like 10 minutes left. Let me thank everyone again that came and everyone that participated and contributed. It was really nice seeing you from a distance. I hope to see you again sometime soon. All right.
Thank you very much, Karim. Let's thank Karim again. And is there any questions? You can ask.